I owe that in big part to our two speakers who are just here. Drs. Allen and Dr. Rodriguez has shared their pathway to becoming people that study the brain in different parts of the science world. Super cool. If you have not already grabbed food, there is extra vegan barbecue, which...
No forks, so you gotta use your fingers.
Yeah, you do have to use your fingers, but
Food's food.
we're big people, so we can probably handle it. So help yourself to what's in the back. Don't worry about getting after class and grabbing some, and there's some drinks there as well. Two more Friends of Medicine seminars the next 2 Wednesdays, 4 to 5:30. There's going to be, next week, there's a guy talking about malaria and someone who's a hospitalist. So you can think about career paths and what that means, what does a hospitalist even mean. And then the week after that is someone who studies the bubonic plague and an orthopedic trauma surgeon who does research. So lots of really interesting people coming through. Super grateful for the ability of them to come and share their time with us and kind of help us get some insight. So we're going to start off. Do I have any announcements I need to make? Is there anything? Oh, I suck. I'll make that announcement first. I asked people to write their names up here if they wanted to me to include them in the survey for extra office hours, and then I forgot to write it down. So if you have not already received an email from me regarding that extra office hours, please just send me an email right now. Just pull out your phone, send me an email, say please include me on that. There's a little survey that just looks for times during the week when it'll work for multiple people. So I sent it to 5 people maybe. Hopefully everyone on that email was actually had their name written down, is from my memory. So please send me an email about that. All right. Any other announcements? Then go. You guys should be able to answer this pretty quickly, right? Go ahead and spend the next 1 to 2 minutes working this problem out. If you get stuck, remember, raise your hand. Lots of people come around and help. And then we're going to build on this for the rest of the class.
I know, I see this in the house, like this together.
That's right.
All right, a couple more seconds. You guys should almost be done.
Where did you get?
$60 a month.
Really? Well,
Different kits though, because there's good and bad things about these that other ones do better and other ones do worse.
it was an adventure.
All right. So, process. Can I have someone step through the process for this particular problem? Volunteers. Or is today a day we start cold calling? David, go ahead.
So first, I found the KB.
Okay. Why do you need the KB?
Because that's how you... I don't know why, but that's the process I've memorized.
Okay, so I'm going to challenge any memorized process. You know that about me.
I hate it.
All right, did you end up using the KB?
Yes.
Okay.
I use that for the new holding action.
So I'm going to say store that for now. We're not going to use KB yet. Why? Hannah? Great. So the first thing you want to do, and hopefully supplemental instruction this week is going to be critical in your understanding of what an acid is, what hydrogen is acidic and what hydrogen is not, because a lot of the hydrogens are not acidic. In this molecule, we have 3 that are not acidic right here. In Orgo, you're going to argue with me about that, but you can come back and we'll argue about those. But the most acidic one, there's no arguing about. It's that carboxylic acid. So we have an acidic proton right here. So we're going to use Ka. So then how do we go about solving for the pH of that, Hannah? Can you keep us going?
Oh, okay.
Process, not the exact numbers. So what's the process you use?
So I wrote down the balance equation.
Okay. Which is Ka or Kb?
Go with Ka.
Are you harassing me because I didn't do aqueous? No, because you should. Okay. You should harass me. All right, so that's Ka. And then what do we do?
I did the rice table.
Fantastic. Do a rice table. Okay, and then what falls out of that? How do we use information?
So you use 0.1 in initial for the product side.
Okay, we don't need to know everything that's in the table. What do we do with the result from the table?
You make a, like, what do I call it, an equation of sorts?
Yeah.
Yeah, an equation of sorts and equal it to Ka.
Does that look right?
Yeah.
Is everyone getting comfortable with writing these out?
Yes.
The result of an ice table. And the reason I still want you thinking about what would the ice table look like is because we need to say, what does that X represent? In this case, Humphrey, what does X represent out of this ice table that we care about to answer this question? Concentration of H3O plus at equilibrium. Okay, that's why we care about X. A lot of other times, X will be the concentration of hydroxide at equilibrium. Is this number going to be 0.100 molar? Is that concentration in this problem going to be 0.100 molar? How do we know that? It's not a strong acid. We need to keep that in mind, all right? What are we approximating the value? It's going to be less than that initial amount. It's going to be less than it by a lot because our Ka is 10 to the negative 5th. So I want you, every time you're going through this, give an estimate. Is it going to be a big number compared to that? Is it going to be a small number compared to that? So make sure that number makes sense. Let's go through other steps. All right? Then can we use the approximation? Should we use the approximation? All right, we're going to approximate that this X is insignificant, the amount that this associates of the total. And then we can solve for X without using the quadratic. Madison, what'd you get for X?
1.34 times 10 to the negative 3.
What's the unit on that?
Surprise. Molarity.
Great. And once again, why do we care about that number? Concentration of hydronium at equilibrium after this acid dissociates. So then can we find the pH just by taking the negative log of that? Is that cool? Yes? No? Yes? Just take the negative log? No? Yes? No? Not sure. You guys should be super clear about this now. Yes. Negative log of this X is equal to pH. All right. Should that number be greater than 7 or less than 7 or equal to 7? All right. Did you do that before you started doing these calculations? Should you do that before you start doing these calculations, David? Okay. So we want to say, is this an acid going to water or a base? Should it be acidic or basic? Thanks for drinking all my rest of my Dr. Pepper there.
Yeah, I do it too.
Nice. I was looking forward to a sip of that, but I guess not anymore.
Sharon, Sharon.
Especially after your voice on Monday was all grumbly. All right.
Share that.
So our final pH was 2 point. What is it, Lindsay? Is it 8.7 or 8.72? 8.72. 3 significant figures in this number. Technically, this has 3 sig figs, but Ka, you can always go look up a more accurate version. So the limitation to our calculations is what did someone measure, and then what numbers are we using that are measured that are not so accurate. That's not so accurate. Yes?
So do we not round the last?
So how many sig figs am I showing here? 3. Not included in sig figs?
You need to round the two.
Oh, so the 2 goes up? Okay.
Depends on how you carry your distance around the X calculation.
So from any calculation before this, you should not round any number at all ever until you get here, and then you say, that's when you decide to round to 3 sig figs. So if you didn't round anywhere, what would that number be? Okay. So I'd have to do it myself. Go back and do all the calculations. By the way, I noticed a number of students are getting wrong answers on their calculators. If you have a calculator or something like this, go into the mode and make sure that the mode is in scientific. One of your options there. Not normal. Because what happens is if you do normal, it only goes to as many zeros as there's room for, and then it rounds. And that's not good. You don't want to round your answer. So it rounds for you. So please put your calculator in scientific mode. Then it'll give you in scientific notation. So maybe that's where the difference came from, right? So then, are we done? Manu, what did I forget? Can you say it out loud? Give me a sentence. We need to check whether the approximation was valid or not. If we do that, what percent ionization happened here? Did anyone do that? So 1.34 out of 100. So yeah, 1.34%. Sounds good. Less than 5% ionization, we can go ahead and use that approximation. You could also use the other one, right? The 100, I don't know what it is. Whatever your homework uses.
So on a test, if we do that to prove it, like if, because it said Ka, well, the mole is 100 times less, whatever, so we do that on the test.
If you do not show that you check the approximation, you will be dinged.
No, I'm saying, would that count as checking the approximation?
Yeah, either one of the 2 approaches, as long as you show me that you check the approximation. 1, you have to do the approximation. 2, you have to show me that you check the approximation. And I would even love to see in the notes right beside, we're putting a weak acid in water, pH should be less than 7. Something like that would show me that you're thinking about it in advance of just plugging numbers into an equation. All right, I'm not going to grade on that, but that if you put that logic flow in place, it will save you a lot of heartache. All right, so we had a lot of different answers. This was the majority answer, so I feel okay with that. I think I have all this written out, right? So we could do a nice table. If we do that, we can make the approximation. Oh, I did have all the numbers written out. So I got 2.872. So that means that if you had the 3, you might have rounded somewhere else. Your calculator might have rounded for you. All right. So our learning objectives for today is going to be one of those days where if you try to skip the conceptual part and just go to the math part, next week you're going to be lost. All right, so we really need to focus, right, Bree, on the conceptual part. If your head's not clear right now, shake it out, go get some fresh air, come back in, because today is a very mathematical day that the concepts are going to drive how we use it and how not to get lost in following steps. If you follow steps, you're going to get lost. All right, so the 2 things I want you to be able to do today: predict the pH of a solution that has a common ion. What's another way to say that? Having a common ion, what does that mean about the identity of the things that are in solution? Are we talking strong acids, strong bases? We're talking about conjugate acid-base pairs. So if you have acetic acid, like we just talked about, you'll have acetate in solution. That's a common ion. Or if we have ammonia, we'll have ammonium in there. It's going to be a mixture of those 2. Does anyone remember what we call a mixture of a weak acid, weak base conjugate pair? We have a lot of both of them. Buffer. So this is where we start talking about buffers. And titrations, which I hear you guys are really good at. So I want you to be able to determine the pH of a buffer solution using a Rice table or using the Henderson-Hausbach equation. Henderson-Hausbach sound familiar? Yes. Hausbach. Makes me think of like really bad German music videos. All right. So the Hoff. It wouldn't be great if the equation was called the Hasselhoff equation. Yeah.
We just short it to the Hoff.
All right. So we're not getting to the Hoff equation yet. What we're doing is we are thinking about the solution that you guys just found the pH of. Now I'm going to say we're going to add something to that. Now I want you thinking about what's going to happen to the pH of that solution. Concept, not math. Don't plug in any numbers, all right? So how is the pH of this solution going to be affected if we add sodium acetate to that solution that we just calculated the pH for?
It's not an acid. It's like an acetate. Sodium's not going to be an acid.
I thought
All right, 10 more seconds, click in your answer. If you're still hungry, please help finish the rest of the food.
No, I don't try to make a trend.
Worst thing, you go to wait a second. Yeah. So I'd rather have you. Huh?
there is a decreasing, I'm sure.
All right, closing up. Or maybe I should stop for a second. This is not a confident answer. What does that mean? Tell me where you guys are losing your confidence on this answer. All right, can I have a couple voices? And this is a part of the class where I need your feedback to help figure out how to make sure to strengthen what you guys are working on. Humphrey. So if you don't know what something is, first you should ask, should I know this? If the answer is yes, write it down and go study it later. What's the second thing you should do then? Look it up. I would do that before asking one of the SI. If they're right beside you, go ahead and ask. But that's a really important realization moment. I should probably know this. If it's a polyatomic ion we're using in this class, this is exactly why I have you guys memorize them. You're not allowed to bring them on the exams. I'm going to have a lot of polyatomic ions on the exams. So you need to have those down pat. It's part of the language of chemistry. You need to know what it means instantly. You need to be able to write down the formula and draw the Lewis structure. Those two things. All right? Yeah.
So we're adding acetate of
Great. So once we have an idea of what it is, and so I'm assuming, before we move on, I'm assuming that's the only problem, is that people didn't know the name. Are there other problems too?
I think the secondary problem is whether it's an acid or a base.
Great. Okay? So that part is what we've been working on, and we're going to continue to work on, but I really hope that you guys start being comfortable in that. And Humphrey, I wasn't trying to harass you. I just wanted to make sure that that's one of those moments where we recognize it's something to do. So if we know, if we look it up, if we do whatever, then we go ahead and we write it out. And we decide whether it's a weak acid, strong acid. That's intense. So how do we figure out whether this is acidic, basic, or neither? Nice and loud, Aurora. Great, so the reason we talk about solubility in this class is so things like this, whenever you see a group 1 or group 1 metal paired with anything as a salt, we almost always say it's soluble. So then we go ahead and we write out the fact that I see it's a sodium means I know that it's going to be able to dissolve. That's if we put it in water. Then what? Colin?
That CH3CO2 negative is going to be taking hydronium out of the water.
So our definition of an acid or a base is going to be a little backed away from that. It's will it pull a proton from water, not hydronium. Just be really careful on that little distinction because that's KB. All right. So we ask each one of these, is this going to accept or donate a proton from water? No. Is this going to accept or donate a proton from water? The answer is yes. So that tells us it's a base. Is it a strong base? What are our strong bases? Some metal, cation, and a hydroxide anion. If it doesn't have hydroxide as a salt, it's not a strong base. A lot of people will see an OH in a molecule and be like, strong base. But that's not the case at all. Remember, alcohols, carboxylic acids. If this were a strong base, a third of America would die every Friday night. That's ethanol. Okay, people drink that to get drunk. It is not a strong base. On the other hand, sink cleaner. That has potassium hydroxide. That's the stuff you pour down your drain when it's clogged. Drano, right? That's a strong base. So let's not mix those two up. If it's not OH minus as part of a salt, it is not a strong base. So then this one we say, okay, it's a weak base. So then how does that help us answer this question? Go ahead and re-poll. Go ahead and click in your response now that we've gone through that process. 10 seconds to click in your answer.
I thought maybe it's two.
Closing out. All right, let's keep us on track here. So we ended up saying that that is going to increase the pH. We have a weak base in water is always going to increase the pH. Doesn't matter what our starting point is, if it's going to increase the pH or not. Yes, but generally speaking, you add a base to water, it increases the pH. You add an acid to water, it decreases the pH. All right? So, big picture, that's the first thing you should always do. So if I ask a question like this, I say, what's the initial pH? Determine above or below 7, acid or not. Acid or base. Second part of the question, you add something else, what's going to happen? Is it an acid or base? Is it going to increase or decrease it? So in this case, we could also say that we're adding a common ion. Right? We're adding a product in this reaction. So what's going to happen to the products as we add a product? It's going to drive the reaction this way. Which means that this, in order to go to the other side, has to consume an H3O+, which maybe is what Colin was getting at earlier.
My question might be a little off topic, and maybe it's something we'll get to later, but like, if you have two weak acids, and one's a little bit stronger of a weak acid than the other, has a lower pH, and you add one with a higher pH, is that going to raise the pH or lower it? It's two acids.
So that is a bit more of a complicated question than we're going to be going to in this class actually at all.
Okay.
So in this class, for the most part, we're going to say it's a single acid with a single base. You might have, your homework had some things where it had a weak acid and a base, a weak acid and a weak base, and it says which is going to have a bigger role in determining the pH. And you have to look at the Ka versus Kb values to determine that if they have equal concentrations. That's a little bit of a different question than what you're asking. That's asking adding acid to an acid, like if we have a solution of nitrous acid and we have acetic acid, is that going to lower the pH? So it depends on dilution and how much protons are dissociated. we could probably calculate those individually and say from each one how much H plus would be added based on what's already there. So it is still a common ion question. So a couple different ways of saying this, right? You add a base to a solution, it's going to increase the pH. You add a product to a reaction at equilibrium, it's going to drive the reactions to the left. But the way that we calculate the pH of the solution isn't going to be, let's find the pH first of just one, and then the pH, how the other one influences it. What we're going to say now is we're going to put both of them in the same solution at the same time, and we're going to calculate the pH. And it's actually much easier to do it that way, to find an exact number, than to find the initial influence of one, and then to find the influence of the other. So, let's do that. Go ahead and try to find out, to calculate what the pH is of this solution. I'm going to give you guys 1 minute just to think about the process. How might you set this up? And then I'll go ahead and talk through how I would suggest setting it up 2 different ways. So try to write down a process that might work for you. How do we use that information? All right. Let me see. Here's some ideas. What types of approaches have you guys thought of? Let's hear it. Bria.
Yeah, so I'm confused because I was trying to like set it up like with the x squared over the concentration, but then I realized that we have sodium acetate, but we also have acetic acid. So I was like, you have a Kp and a Ka, so I didn't know what I was supposed to use. Okay, great. So that's where a really great example of where it is that you would actually write out the ice table and not just x squared over initial minus x. If we do that, is there a place for both of these? So whenever we have a salt, getting to Kayla's point, if we ever see a salt as part of the problem, do a separate little equation to say what happens when that dissolves, what are the things that it dissociates into. And then you say, are any of those part of this equation here? If so, you put them into the ice table. You can put them into the ice table. Can someone explain how I was able to put both of those into the ice table? Corbin? Was that you raising your hand? Kalia? Nice and loud.
When sodium acetate dissociates completely with salt, you have complete. The concentration of the salt is concentration of the base.
Okay, and then how does the base acetate fit into this table? It is the concentration of the conjugate base. Right, so we have acid and base have the same conjugate acid, conjugate base, have the same concentration. So then the question is, what's going to happen? What change is going to occur? Talk to your neighbor and decide what we put in each one of the change columns here. The change row. And define why. I want to know why you do minus or plus on either side. Thanks, Corbin. All right, I want you to raise your hand if you think the left side is going to have a plus x. Is this going to be plus x? Raise your hand right now. Right, the left side is plus x. All right, raise your hand if you think it's going to be a minus x on this side. That's the majority answer. Why? Why might you answer that? Okay, so what is the opposite of your answer? So your answer is the left side has something in it. By definition, what about the other side? If you write out your value, what value are we talking about? K? The initial value is at K. Q? Q. All right. So Q is concentration of products over concentration of reactants. We have 0. If we're talking about Gibbs free energy diagram, we're all the way over on the left. Even though we have some of one of the products, we have 0 of the other. So there is no way you can use up these two to make this because there isn't one of them. You can also say that Q is less than K. So you're going to have to produce something on the right side. That's the only way you can get to a non-zero value of Q, and Q has to get to K. So then we're using up our reactant to generate what's the product in this case. Does that work? All right, so then let's go ahead and write out our Ka like normal, right? Who loves a quadratic? How do we avoid quadratics?
Nope, you won't do that. Write it on the test.
All right, so conceptually, let's think through this now. Normally what we talk about is that the amount of this, with nothing here, the amount of this that dissociates to get Q equal to K is really small. How do you think that's going to be influenced by having something already as one of the products? Is this X going to be bigger or smaller than if we didn't have anything over here? It's going to be smaller because there's already something here, so that means this X has got to be super small. Super small. So very little of this is going to dissociate. So let's go ahead and make that assumption. So go ahead and do that on your own. I want you to finish this problem and tell me what the pH of the solution is based off of assuming that both of those X's are negligible. You guys know what I'm asking you to do? Find the pH, making the assumption that both of these changes in concentration are negligible. Can you do that? Do you know what Ka is? It's the same acid, still Ka the way it's written, so you know Ka. Does your life become easier or harder than a regular problem now? So click in the pH. Click in the pH. Her calculations. I was just looking at them. All right, a couple more seconds. I didn't clear mine. I just looked at what she had. All right. All right, closing out. Am I going to want to look at these answers?
Yes.
10% of our votes are unchanged. We have 35% of our votes are 4.745. Some other variations of those sig figs. All right, so we have a number of answers. Let's go ahead and flush this out, right? So hopefully you guys are comfortable with algebra. Same number on the top and the bottom. It's not minus anything plus. We can't do that here, right? Because one is a little bit bigger, one is a little bit smaller. Those things don't cancel out. But now we can. So then Ka is X. That means your concentration, right? X is the concentration base 0 plus at equilibrium. That is Ka, 1 times 10 negative fifth. Estimate what the pH is off of that. About 5, but it's a little bit above 5, closer to 4. So it's going to be between 4 and 5, right? Because it's somewhere between 1 and 10 would be 10 to the negative 4. So if I go ahead and take the negative log of that, 4.745. 3 sig figs, 3 past the decimal. So what just happened? Didn't you do any of these calculations? I just give you Ka and you find the pH. Done. Why? Only if the concentration of the conjugate acid and the conjugate base are exactly the same.
And if that wasn't.
Does that sound familiar? Where does that sound familiar from?
Titration lab.
From titration lab. What's that called? Is that the equivalence point?
No. It's a
Half the equivalence point. The equivalence point is where you have used up all of your initial analyte with your titrant. All right, we're going to spend the next week getting into that, building up what we've done in the lab. So I'm very grateful to your TAs in the back for guiding you through all that.
question.
Yes?
It has to be a salt too, right?
So in order for what we just said to be true, the most important take-home is it must be a conjugate acid-base pair. So it has to be the same. This has to be a conjugate of that. If those are not conjugates of each other, we can't use this. We're done. Totally different problem. The second thing is that the concentrations of them have to be equal. All right? So that can be a weak base and its conjugate acid. It can be any weak acid and its conjugate base. As long as we have that conjugate acid-base pair, then this works.
What were the two clauses?
Has to be a conjugate acid-base pair. If it's something with 3 protons, so for instance, it would not work if you have these two in solution together. Why not? Christina? Conjugate has to be a difference of 1 proton. There's 2 protons different between these two. It's not a conjugate acid-base pair. They're related through 2 conjugate acid-base pairs, right? There's a compound in the middle that's a conjugate acid base with this, and also with that, but they're not with each other. All right. Wouldn't it be nice if we also checked our assumption? What do you notice about that? Is that close to 5%? All right, so when we talked about before, let's approximate. Is this 0 going to get much bigger or not? We say that if there's 0, 0, so little of this is going to dissociate to less than 5%. And then we already have a ton of this here, so that means that this is going to be a really, really, really small amount that it dissociates. So that validates our assumption, and we're okay to move forward. This is kind of time-consuming, right? You have to think about, like, how does each one influence? We've got our noise table. Wouldn't it be nice if there's a quicker way to do this? What is it?
I just walked in.
The Hoff!
Oh, the Hoff.
Come on, I pointed at you for one thing in class.
We were talking about half earlier, right? So that was the Ka. Isn't that
All right.
half the pH of it earlier?
You came in right in the middle of that, so we'll catch up to the side. But that wasn't exactly what I was getting at that point. All right, so the Hoff equation, it's not the Hoff, it's the Bach, but it allows us to calculate this, but get this. Those assumptions that we just made are built into the equation. That means that we're using an assumption that the assumption is valid every time we use this equation. So we have to be a little bit careful with that. So what I want you guys to do, another idea, thought about it. You can plug in your x value and make sure that everything lines up and everything works. And And that also verifies our answer. So if you're ever not sure, 100% sure that your answer makes sense for x, plug it back into your Ka equation, and you can double check yourself. So what I want to do now is talk about the Henderson-Hasselbalch equation. Where does it come from? How do we use it? How does it simplify our lives? So go ahead and rearrange this equation so that you get H plus or H3O plus on one side by itself. What does the rest of it look like? This is something that we have on the placement test for this class, so I hope that you guys are very comfortable rearranging equations. You guys didn't all take it? Oh, 1402, sorry. No, the placement test for this class is 1402. All right, a couple more seconds to rearrange this. Can I get a volunteer? What is this equation rearranged when you have is equal to H3O plus? New voice, new voice. Bree? Brianna?
H3O plus is that equal to Ka times the concentration AK over
A minus. Great. Then what happens if we take the negative log of both sides? All right, so we're going to use rule of logs. You guys took a quiz on this, which means that you're now masters because you got it back and you understand. So I want you to separate everything on the right side. So on the left side, what is it? Negative log H3O plus, what is that? pH. All right, on the right side, I want you to go ahead and write out how does that influence each of these three. And actually, let's just do how does it relate these two to each other. You can do this all together as one if you want. So it's the negative log of something times something. So we're going to do pH equals negative log of Ka plus negative log of or
Negative log of H3 minus negative log of A minus. Division of log of minus.
so there's a plus minus in the middle there. So what does that give us in the end? Minus. So then let's simplify this. So pH equals, what's negative log of Ka? pKa minus is this the Henderson-Hasselbalch equation? It's actually really close. There's only one thing that's usually done different. So, rule of logs, if you change this sign, it flips the fraction. So let's go ahead and do that. Oops. And voila. The Henderson-Hasselbalch equation. Some friends in German there. All right, that's it. That's the whole equation. So, how do we use this?
So, from what I watched on a video, it showed that if you have the equivalence point, half of that is it showed that basically your acid and your base divided by each other would equal 1, so the negative log of 1 would equal 0. So if you add pKa plus 0, then you just need your half of your pH to equal pKa.
So you're exactly right. And you are also about a week ahead of what we're doing in class, but you've done it in lab. And so really quickly, yes, and in some of your homeworks. So really quickly, if you have a weak acid, what would you add to that in titration to give you the conjugate base? if you wanted to use up this to forcefully make your conjugate base, what would you add to that? You have to add a strong base. So one of the things we're going to be talking about at the beginning of this class, and actually on your homework a little bit, is that strong base, if it's ever in the vicinity of any acid, doesn't matter if it's weak or strong, is always going to use it up 100%. Becomes a limiting reagent problem. You guys love those from first semester, right?
No.
And from lab. So, let's say that we have 10 moles of this, and we have 5 moles of this. It is a limiting reagent problem. It is not an equilibrium problem. So, if we have 10 moles of our weak acid, 5 moles of the strong base, which one's going to get used up first? So, this is actually, let's not do that yet. So we're going to use up 5 moles of each, and our products are going to be, any questions on how I got those products? We have an acidic proton, we have a strong base. OH minus, H plus together makes water. What's left over here when we take that H plus away? Whatever that conjugate anion is. All right. So let's say we don't have any of those really, and we don't really care about water, right? When we use up 5 of these and 5 of these, what are we left with? And then what did we make? Okay. Is this the equivalence point of a titration? This is exactly halfway. What would this number of hydroxide moles be to get to the equivalence point? You guys remember in lab, right? If you equivalence point means an equal number of moles of your reactant, your analyte, and your titrant, based on the stoichiometric ratio. So, if it's a 1-to-1 ratio, it means you'd have the same number of moles of each. That is the equivalence point. We only got halfway there, right? We only used half of them up. But now we have a mixture that's 1-to-1, which is exactly what we had in the last problem. So there's 2 ways to make a buffer. Both of these are buffer solutions. One is you just pour both of them into solution, the weak acid and the salt of its conjugate base, right? The sodium acetate. The other one is if this is acetic acid, then we add some hydroxide, sodium hydroxide, potassium hydroxide, whatever that is, and convert half of this to the conjugate base. When we're at that point, the half equivalence point, pH equals pK. And that's what you guys are doing calculations of this week in lab. Isn't it this week? And last week, is that what you said? Okay. So, in our Henderson-Hasselbalch equation, let's think about what these numbers mean. If we're at the half equivalence point, and we have an equal concentration on the top and the bottom, Josh was getting at this earlier. What is this number? 1, same concentration top and the bottom, and log of 1 is 0. pH equals pK. What's behind the scenes in that thought process is an ice table with the assumption built into it. So you could do the exact same thing. So if we used our numbers here from that last problem, pH equals 4 point, what was it? 872? 7, okay, totally wrong. Plus log of 0.100 over 0.100. Notice how these have the assumption built into them. Right, there's the minus x, is irrelevant. We're not going to use it, otherwise it'd be a much more complicated thing. The Henderson-Hasselbalch is a really, really nice way to work. In what cases, maybe I have you guys discuss this in your groups, when does the assumption not work? Talk to your neighbor and try to get some ideas of when the assumption doesn't work. If you're doing an ice table, what are the times in which the assumption fails and we have to use quadratic? Conjugate acid base pair, you have to have both. So there's ways to make it that involve a strong, but the end result can't be a strong. All right, can I hear some thoughts on when it is that the assumption fails? Go ahead, Kayla. The assumption can be valid if the assumptions are different. It just might be a twofold instead of a one-fold different. So if you're at 2.5% ionization for one, 2 of it would put you over the assumption. So that might play a role. A lot of times it's an order of magnitude or 2 different, so it doesn't necessarily play a role. What are some other times that the assumption fails? You guys have worked on problems, right, in homework problems where you had to use a quadratic. Ruby?
When the percentage of what you calculate is more than 5% of the original molarity.
Great. When the percent ionization is more than 5%, when does that happen? Strong acid. Great, that's one example where you could not use the Henderson-Hasselbalch equation. And just as a general rule, Henderson-Hasselbalch equation only applies to a conjugate acid-base pair. If you don't have a conjugate acid-base pair, you cannot use this equation. This A has to be the same as that A. Otherwise, this is irrelevant. And this can't be a strong acid. There's another form of the equation, and I don't want you getting stuck on versions of the equation, but if this was a base instead, what would go on the top and what would go on the bottom? What if it was ammonia and ammonium? What would go on the top, what would go on the bottom? What would go on the top, what would go on the bottom? I hear NH3 on top, NH4 plus on the bottom. Perfect. I don't care whether it's a weak base and it's conjugate acid or a weak acid and it's conjugate base. The basic one goes on top, the acidic one goes in the bottom, and then we use pKa. Done. Don't try to make this complicated. Don't try to use pKb and then we rewrite the equation. If you go through all these steps and use Kb, yes, there's a version of it that uses Kb. But you don't need to do that. You just need to use pKa, this ratio, this setup. Okay, so let's go back to the 5%. If it's more than 5% ionization, the assumption doesn't work. So when else do we have a really high percentage ionization? Strong acids. What else? Strong bases, but you typically don't use ice tables for those. What about concentration? Does concentration play a role in ionization? Yes. Is it if it's really concentrated, there's a high percent ionization? Or is it if there's a low concentration, it's a high percent ionization? You guys remember? If it's dilute, the more dilute the solution is, the higher the percent ionization is. You can think about it this way. If you have an acid, this is not really an acid, right? But if there's an OH, it's in solution, it's running into its conjugate, so when it runs into another conjugate, it's going to take us back. If there's a lot of both of these floating around, there's a higher likelihood that they're going to bump into each other. If there's a very low concentration, they're going to fall apart, then they're going to stay apart for a longer percentage of the time. So in a weak solution, you have a lower percent or a higher percent ionization, they stay apart more of the time. So that means that if this number is really small, or this number is really small, then you can't use the Henderson-Hasselbalch. And the rule, the simple rule here, is that if it's 10 to 1, or 1 to 10, or anywhere in between those, you can use the Henderson-Hasselbalch. But if it's outside of that, if it's a 20 to 1, you can't use it. If it's a 15 to 1 ratio between the two, you can't use it. Because the one that's on the one side is dilute compared to the other, and you're not going to be able to use the Henderson-Hasselbalch for that assumption. Okay? So here the 10 to 1 ratio, that's what it's talking about. Is that whatever you have to have some of both and a decent amount of both. All right. You guys want to try using this? All right. Go ahead and type in what the pH of this buffer solution is. And then make sure that you can describe why this is a buffer solution. If you get stuck, raise your hand. And we have two responses. Raise your hand if you're stuck. Now's the time to not sit there and wait on Alright, how are we doing? 6 more seconds. Okay, 30 more seconds. So the Henderson-Hasselbalch allows you to shortcut this whole thing if you know it's a constant space there. So use the Henderson-Hasselbalch, And then where would you use what values? So write out the Henderson-Hasselbalch right here. And then think about what values you know and what you need to solve for. All right. Can I hear from one of the four ladies right here, from Schneider over to Chelsea? One of you guys in that group. How did you approach this problem? Why? How did you determine that you could use a Henderson-Hasselbalch? What were you looking for? Okay. Can someone help add on to that? How would we know? Echo?
Because I started doing the ice chart, and then whenever I solved for x, I realized that x wasn't significant enough to actually change
So pause. Before you even go down that road, there's a big step that we're skipping over. Hannah, what is that?
Isn't it a conjugate base pair?
You have to decide whether it's a conjugate acid-base pair first. And some of you might have just skipped and I'm assuming it is. Or you knew it was and you just didn't describe it. So, right, we need to make sure we identify that first. So, do we have an acid? I showed the structure of one of the compounds there. What functional group is present in that molecule? Carboxylic acid. Has the word acid in it, right? C double bonded to O with an OH attached. It's going to be acidic. Formic acid. Then the question is, what is that other compound? So I have it written out formula-wise up there, but it's only the name on your paper. So you need to once again know formate is a polyatomic ion. Or if you look here, what's missing between these two compounds and what's different between those two compounds? This H that's attached to an oxygen on a carboxylic acid is now a potassium. So we would say HCOOK goes into water. Well, no need necessarily to do plus. And you get HCOO minus and potassium, both of those aqueous. So then we say, well, that looks like the conjugate base of that. Right? That's the process I need you all to go through first before you plug numbers in, because those numbers might not always get you where you need to go. I might have had potassium nitrate up there, and you'd be like, turns out it's just a weak acid in water. So don't make those assumptions. Okay. And then, now that we have a conjugate acid-base pair, we can either do what Echo was talking about and do an ice table and start with both at the top. What's the simpler way to do that? Plug and play in the Bach. pH equals, did anyone calculate our pKa for us? Plus log of what over what? Which one's on top, which one's on bottom? Base on the top or on the bottom?
What threw me off is I didn't know if those concentrations were the initial added into the solution together, or if it was at.
Great question. So as you're starting out, all of the concentrations, if you're given for a weak acid problem, what's the pH of 1 molar or whatever, or if you're given a mixture, that's always the initial concentration. And that's what goes in the top of an ice table. That's what goes here. It means that most of the time they're going to be the final concentrations as well, because we assume that the dissociation is very small. We can go check that later. Once we have our pH value, we can compare it to this guy and see what percentage of that would that be. All right, so before we do any calculations, what range is the pH going to be in? What are we comparing? What's a realistic pH value? Talk to your neighbor. What point are we comparing to be higher or lower than? What's a reasonable number to compare higher or lower for this calculation? So I heard a number of people say we would compare this to a pH of 7. Is it higher or lower than 7? Is that right?
No.
No. Why? What are we comparing it to? It's higher or lower than what? Say again, who was that over here? Not the Ka, the exponent on the Ka, or specifically the pKa. So, pH equals pK, this equals that, when what's the ratio here? They're equal to each other, right? So we know that if there's more of one than the other, it's going to be a higher or lower pH than the pKa. What is it in this case? Do we have more, which one do we have more of, the acid or the base in the conjugate pair? So is it going to be a higher or a lower pH than pKa? Higher. All right? Before you do any calculations, please estimate before you do any calculations. If you get a number, you might accidentally flip this, just because you're working quickly, whatever it is, and you get a pH of 2.7. Wrong. You should know right away that you made just a simple flip error. That's it. I can guarantee you on the exam there will be questions like this, and I will put the answer of the flipped version there. You have to do it because I want you guys to check your answers, right, whether it makes sense or not. So I know that the pH is going to be higher than the pKa because there's more of the conjugate base than the conjugate acid in this pair, meaning it's more basic than an equal mixture of the two. So we could do the whole ice table, or we could do the Henderson-Hasselbalch. And I got a pH of 4.01. Does that sound about right? I saw that as one of the answers, but maybe not the top answer in there. All right, we have a couple more minutes in class, and we're going to get through all of these. You guys have an idea of how to use this, right? All right, so the last problem on your worksheet, the last set of problems, questions 7 through 10. I want you to use the information presented here. Click in the pH for question, this is 7, I believe.
Yes.
So we're going to go through these relatively quick. So you got about 2 minutes to do the first one. We're going to do less and less time for each of the following ones. Estimate first, then do your calculation.
I was looking at my last. Let's say I just like to say which one. Yeah.
You're talking about where this weak acid and this one base is so let's talk about that. What's the base of Ka versus Ka is a bigger number. That's going to tell you.
Yeah.
So it's like
Yeah.
So what does that tell you? So think about this. pH is their same concentration. So write it out. Just write it out. pH equals plus. Think about, is it a conjugate acid base pair? Do that first. And then for the concentrations, which is the acid, which is the base. So you need to speed up, put them in place. All right, closing out. So what are the steps? Can I have a volunteer to go through the steps? Hopefully a new voice. New voice, new voice, new voice. Anybody? Avery. Before you did that, very, 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 very first thing.
Oh, I set up the whole to see if they were actually a conjugate.
Well, we don't even have to set up an equation. We just have to say, is this a conjugate acid-base pair? We have acetic acid. We have acetate with a sodium ion. Yes, it's a conjugate acid-base pair. And then?
So then, there's less base. I said pH is less than pKa. I looked at the pKa 4.75. And then I put that into the equation. So pH equals 4.75 plus the log of 0.25 over 0.50. And it was 4.45.
Is that what you guys got? All right, so let's bring everyone together. We only have a couple minutes left of class. We're going to try to go through these, and hopefully doing repetition will help, and then you can practice on your own. So Avery's approach was fantastic. She said, determine it's a conjugate acid-base pair, check. Now we can use a Henderson-Hasselbalch because these are less than a tenfold difference in concentration. If this was 0.025, we'd have an issue. Then she said, well, there's more of the acid than there is the base. So it's going to be more acidic than pKa. And then she did Henderson-Hasselbalch to find that number. All right, let's go ahead and do the next one. Is everyone okay with what this name is telling us? Ammonium, ethyl ammonium. It has a positive charge on the nitrogen. It has an extra hydrogen on there in this case. It's not 4 hydrogens because it has an ethyl group on there, but it has 3 hydrogens and a carbon. Is that going to be an acid or a base? Ethyl ammonium chloride, is this the acid or the base?
I thought that was the acid.
Ammonium, nitrogen, positive charge, has a hydrogen, has a counter ion that's a chloride. Ethyl amine, is this an acid or a base?
It's the same ratio, doesn't matter.
All right, we're just about out of time. Is the pH going to be higher or lower than pKa for this problem? I hear higher and I hear lower. What do we have more of, the base or the acid of the conjugate pair? We have more of the base than the acid, which means pH is going to be higher than the pKa. Is this the pKa? Can we find the pKa from the pKb? So the pKa is what, 11-ish? 10.81. So pH is going to be higher than 10.81. Is that what you guys got? All right. Go ahead and do the last two as practice. We are out of time for today's class. I want you to be able to go through this really quickly and spend very little time in class on this. You have some homework problems that I've yet to post because Al is a piece of junk right now. It is not letting me generate the homework problem, so when I do, I'll email you. Should be tonight. A homework?